Hello. The gravitational effect. Light speed motion in the same direction as compressed field fronts causes gravity. Only the most highly compressed electromagnetic field fronts can travel between atoms. 10,000 times compressed fronts only happen in front of 99.99% of the speed of light quarks. So it has to move that fast for the most compressed part of the field that it makes to be 10,000 times compressed. If you want it to be more than a pinpoint, then you have to pick up the speed to 99.995% of the speed of light. And at that speed, you have roughly 2 degrees from the center in all directions. So it's a little spot ahead of the quark as it goes in a circle. As it circles, there'll be a little spot which is compressed enough. And it falls off pretty quickly. If you go out, say, another degree, so instead of 2 degrees all around, 3 degrees all around, it drops off by about a factor of 10. So it's only the field in a small area in front of quarks, and only quarks moving at very, very close to the speed of light, which can possibly, well, they're much stronger than any other field because they're so compressed, and only they can produce gravity. Now, when a quark moves in the same direction as the front that other quarks have created, so other quarks create this, a quark creates the front, and it moves away from the quark. It's compressed, and it's moving at the speed of light, and it's moving directly in the direction the quark was going. And when it comes to another quark, if the other quark is going at exactly the same, in the same direction, if it includes the same direction in its motion, and gravity actually causes quarks to align this way so that quarks will include the primary direction of gravity in their motion. They'll include that direction, so that when they both are moving at this, then you have a prolonged interaction. You have a very long interaction between the quark and the field front, because they're both going about the same speed in the same direction, so that it's even though it's an incredibly short time, it's much longer than it would otherwise be. And the gravitational effect is basically when this field front, they have the same sign, is moving in behind the quark, it's pushing the quark, and the quark will it will not respond normally. Normally, when a compressed field front comes upon a charge, it pushes it one way, then it pushes it the other way. And if the quark's not moving fast, then it pushes it roughly equally both ways. For example, electrons get pushed one way, then the other way. And no matter what direction the electron's going, it's the same effect, pushed one way, then the other way. The most prolonged effect upon an electron would be when they're going in the same direction. But again, it's just a push one way, then the other, because it's well below the speed of light, and it has no restrictions to be pushed one way, then the other. But in the case of a light speed quark, the gravitational effect is it pushes upon it, but moving in that direction already at very close to the speed of light, it cannot speed up. So it does not get a push in the direction the field is moving. It's already going at the speed of light in that direction. It resists it totally. And then as the field as the front passes it, the compressed front passes it, it pushes back against the quark normally. And since the quark is tied to the other two quarks in its motion by chromodynamic bonding, it is pushed back, and that's gravitation. The fact that in one direction it resists it because it's moving close to the speed of light, and in the other direction it is normally pushed back in a normal way. And the net effect of those two is back towards the direction the front was coming. That's your gravitation.